Okay, cool. So this is the next question that we got on the menu today. It is presenting this situation where we have a point charge called Q at the origin. A particle of mass 2 grams carries a charge of 15 microcoulombs. The particle is released from rest at x equals 1 meters, and its kinetic energy as it passes 25 centimeters is 0.5 joules. What is the charge Q? Okay, so let's actually draw a diagram to represent the situation here. Keep in mind here it says 1 meter and 25 centimeters. Okay, that's a very important thing because otherwise we would have a very wrong answer. Okay, so keep that in mind. So let's draw the situation. We have our point charge Q, and this is at x equals 0. Oops. Okay, so let me just draw out what I imagine 1 meter might look like. Oops, can't count these grid lines. Okay, so this would be 1 meter, and this would have to be 0.25 meters or 25 centimeters, and this is 1 meter, this is 0 meters. Okay, so these are the distances, and we have a particle that initially starts at x equals 1. We have our mass is equal to 2 grams, which is equal to 0.002 kilograms. And our charge is 15 microcoulombs. Another way that we can write that is Q is equal to 15 times 10 to the negative 6 coulombs. And here we are starting at rest. Okay, so our initial velocity, our VO, is 0 meters per second. And once we get to here, like we're moving at this point. Oh, also the charge is negative. Whoops, that's my bad. Oops, I'm gonna need to find a nice way to give myself some space. Okay, so when we get to this point, it has a kinetic energy of 0.5 joules. Okay, so these are all of the things that were given. This is a pretty good representation, and we're trying to solve for Q. So essentially what we need here is our we want to be thinking in terms of energy, right? Because we were given an energy value, and we know that we have you know, a lot of things that could help us lead to a bunch of energy values. So that's the way that we want to proceed with this. We want to think about the conservation of energy. Okay, so in this case, it's all going to be we have our initial potential energy, so PEI, plus our initial kinetic energy, but we actually don't have a kinetic energy. 0 starts at rest. And we're going to equate this to our final potential energy, PEF, plus our final kinetic energy. And we're already given our final kinetic energy, so we don't really need to calculate that. I mean, we could if we wanted to, but we could also calculate the speed if we wanted to, but that's not what the question is asking, so let's just focus on what the question is asking. So let's pretty much is just going to be the change in potential energy that results in this kinetic energy popping up. So we want to sub out some of these equations so that or some of these terms to get their actual equations. So we know that the potential energy of a charged particle is going to be kq over kqqq over r. Okay, that's the potential energy. So let's call this RF, and this will be RI for our final distance and our initial distance. So our initial distance will be our initial potential energy, kq big Q little q over R initial, is going to be equal to k big Q little q over R final plus well, simply 0.5 joules, because that's what was given to us in the equation, and we're trying to solve for big Q. Okay, and we know that big Q has to be positive, because since a little q is negative, they're going to need to be opposite signs so that little q is attracted to big Q, because they're getting closer to each other. Okay, so let's bring this term to the other side of the equation. So we're going to have k big Q little q over Ri minus k big Q little q over Rf is equal to 0.5 joules. And we want to factor out big Q, because that's what we're looking for. Oops, let's make this J a little bit more pretty. Okay, so we'll actually factor out the K and the both Q's. K big Q little q 1 over Ri minus 1 over Rf equal to 0.5 joules. And to isolate for a big Q, we will need to have 1 over k little q times 1 over Ri minus 1 over Rf times 0.5 joules. Okay, so let's sub in our values here. 1 over 9 times 10 to the 9, that's our K. Our Q value was negative 15 times 10 to the negative 6 coulombs. Our initial was 1 over 1 meter minus 1 over 0.25. That's our final distance. And on top here we have 0.5. Yeah, just that. So let's run through this calculation. So 9 times 10 to the power 9 times 15 times 10 to the power of negative 6 times 1 inverse minus 0.25 inverse the reciprocal of that times 0.5, and my result for this is a positive value 1.23456. This is too perfectly set up. 1.2345679 times 10 to the negative 6 coulombs. That's like way too perfect of an answer. That's pretty beautiful. And since we have it came out to a positive, so we can actually rewrite this as Q is equal to how many significant figures do we have here? So we got one significant figure here, so unfortunately we do got to cut this off at just like 1 microcoulomb, positive 1 microcoulomb to 1 sig fig. Okay, so that would be the answer, and it has to be positive because it's attracting the negative charge into there. Okay, so yeah, cool. So sign error. Answer is good, just needs to be positive. Cool.